Hello everyone. So let's wait for a couple of more minutes so that others can join, and after that we'll start today's session. Can someone confirm if I am audible? Hello. Hello. Am I audible?
Yes,
So we'll wait for a couple of more minutes so that other students can join, and then we will start today's session. Yes. It's 3 p.m. already, and I think we can start our session. So can someone confirm if my screen is visible and if I'm audible?
it's visible.
Okay. So let me briefly introduce myself. So my name is Arpit Bal. I'm a PhD scholar at Department of Electrical Engineering, IIT Bombay, and I'm an NPTEL PMRF TA for this course, PMIC. Uh, so my research topic is analog front-end design for neuromodulation applications. So currently, I'm pursuing my PhD under the guidance of Dr. Lakshmisha Somapur from IIT Bombay. Okay. So previously, I was NPTEL TA for some other courses like digital IC design, which was taken by Professor Jankiram. Then analog electronic circuits, which was taken by Professor Shauribrata Chatterjee. Then digital electronic circuits, which was taken by Professor Shantanu Chattopadhyay from Kharagpur. Okay. So let me briefly tell you about the motivation behind these live sessions. So these live sessions are to solve few numerical problems. So what we will be doing today is like we'll have a few numerical problems and we will try to solve them. So we will be solving them together. Okay. So what I suggest others is to grab a piece of paper and a pen. So whatever question you see, so we are going to solve it together. Whenever you have a doubt, feel free to unmute yourself and ask me the question. Okay. So each week, the topics that we will be picking to solve for that particular week's live session will be related to that week's content. Okay. So So what I'll suggest is like first you should uh, go through the week one's lecture content, and then you can join the live sessions where we will be solving problems, and they will be helpful to you. Uh, I mean, they'll help you to solve the assignment questions as well as the questions in the exam. So it will be kind of a practice session for you. Okay, is that clear with everyone?
So I have a doubt that is
Yeah.
there any prerequisite knowledge required for this subject? Like only analog electronics would be enough, or any other
Yes. Yeah.
subject is
Actually,
possible?
analog electronics will be enough. So yeah. So this is a good question. So many students have a doubt that is it related to, like, do we need to have a background in power electronics or something? So the answer is no. The only basics that you need here is basic electrical circuits, like circuit analysis plus analog electronic circuits. I think that will be enough to get you started with the course. Does, does that answer your question?
Yes, sir. Thank you, sir.
Okay. So, with that brief introduction, I think we can start today's session. So, before starting, is there any other question that anyone has?
I have one question.
Yeah.
Can you suggest some reference material or books to follow along with this course apart from Razavi?
Apart from Razavi. Okay. So there is a book. So for OPAMP related stuffs, right? So there is a book by Sergio Franco. So you can refer to that. The book's name is Design with uh, Operational Amplifiers and Analog Integrated Circuits. Okay. So so you can refer to that voltage regulator. So there is a chapter called voltage regulator in that one. So I think that will also be quite useful for you. Okay. Okay, so let me briefly talk about this field of PMIC, and it's currently a very hot topic. Okay, so uh, with rising demand of integrated power management circuits, so maybe I mean starting from your mobile phone to uh, large computing systems, everything needs power management. Okay, because indirectly it is going to affect your system's performance. Okay, so let us say we are trying to capture signal from a sensor, right? So the output, I mean the starting from the ENOP or the clarity of the signal, it depends on how clean your power supply is. Okay, so that indirectly refers to your PMIC block that is present there. It has to be as good as possible. Okay, because you are going to have digital circuitry and analog circuitry sitting next to each other. So the digital circuitry can, uh, cause disturbances in the power line, and that indirectly affect analog. And so this is just a brief motivation for the PMIC part. Okay. Okay. Let us start with the first question. Okay. So, so this is our first question. So a switching regulator operates at an efficiency of 88%, which V in equals to 1.7 volt. Okay. And V out is 1.1 volt, delivering a load current of 600 milliamps. So what is the total power? Okay. So please try to solve it on your own. Then we'll give you the solution. Okay. So I'll briefly give you a hint that your efficiency is P out by P in. Okay. And your P out is equal to P in minus Qs. Okay. So can you try to substitute it and find out what is the P loss? So in this equation, what is the known variable that is present here in question one? Yeah. Okay. So we have one answer. Is there any other answer? Okay. So yeah, the answer that is present in the chat box is correct. Okay. So instead of directly using the formula, let us say I just write it as P out, P out plus P loss. So this thing comes from here. Okay. This implies my theta. Let me directly write it as VT by 100 equals. So my P out P out plus X. Okay. This implies P out is equal to 0.88 P out plus 0.88 P loss. This implies 0.12 P out is equal to 0.88 P loss. This implies my P loss equals 0.1258 into. So what is the P out? That is our V out into the load current. It is 600. Okay. So that comes out to be, yeah, both the answers are correct. That is 19. Okay. Is this question clear or is there any doubt in this question?
I have one doubt. Since a switching regulator is there, we can
Hmm.
assume it's either a DC-DC buck or boost.
Hmm.
Use the formula in terms of P input,
Hmm.
where P loss is equals to 1 minus eta into P input, like
Yep.
rearranging this thing.
Okay.
So what will be P input? It cannot be V input into 600 milliampere because that's the output current.
Uh, no. Yeah. Yeah. That's a correct observation. So that is why you must have seen during the lectures, right? So we mostly focus on the P out whenever it comes to switching regulator, right? So
Okay,
unless
so
it is given to us, yeah,
in one of the example where sir took V out P out I output equals to I input, their linear regulator was given, so that's justified.
yes, yeah.
Okay, yeah, thank you.
Yeah. Okay, is my screen visible? Because I got a message that there is some internet issue.
It's visible.
Okay, so I'll pause here for 1 minute so that you can note down the solution in the method. Okay. Okay, so one more thing. So the session is being recorded, and I'll upload the recorded video on the Teams, sorry, not Teams, on the YouTube channel. Okay. Okay, so P loss is equal to 90 milliwatt. Okay, so there is a small question here. So from the lecture, you must have seen that switching regulator offers higher efficiency in comparison to a linear regulator. Okay, so can someone name any disadvantage of a switching regulator?
Output voltage ripple, larger area.
Okay, okay, that is one. Any more?
Any critical situation or any critical circuit, like if you use some switching regulator, there is some switching harmonics also present.
Yes,
So based on this, switching harmonics can also disrupt our subsequent systems in the circuits.
exactly, exactly. Yeah. So that is also another point. So whenever you have a very noise critical circuit, okay, that is very sensitive to noise. So switching regulator is, I mean, regulator should be avoided in that case because of the switching noise that is being injected. And in that case, we go for linear regulator. Okay. Okay. So we are done with question one. Let's move to question two. Okay. So the question two is this: power management module comprises of two regulators with the following specs. Okay. So the supply is given here, 2.5 volt supply. Regulator 1 is linear, whose V output is 1 volt, and the I load is given as 180 milliamps. On the other hand, the switching regulator V out is 1.8 volt, I load is 1.8 amps. The efficiency of switching regulator is given as 90%. Okay. So we have to find out what is the total efficiency of the power management module. Okay. Add a page here. Okay. So please start solving this, and if anyone comes up with the answer, please post it on the chat box. Okay. So I'll give you 1 or 2 minutes, then I'll start solving this question. Yeah. Yes. The answer. Okay. Let's wait for any other answer. Okay. I'll wait for 1 more minute, then I'll start solving this. Okay. We have two different answers. So just remember, you have to find out the total efficiency of the power management. Okay. Okay. So let us start solving it. Let's see. So what is the P out in this case? It is 1 volt into 180 milliamps. That is nothing but 180 milli. And what is the P loss? So the P loss is 2.5 minus 1 into 180 milli. Okay. So that is 1.5 into 180 milli. That is 270 milli. Similarly, for the switching regulator part, our P out is 140 and 120. That is 3.24. Okay. And what is my P loss? That is equals to 1 by eta minus 1 times P out. 1 minus eta is 90%. 0.9 by 0.9 into 3.24. That comes out to 0.36. Okay. So my eta, let me call it eta net, is equal to P out total by P out total plus P loss total. Okay. So my P out total is nothing but the power output from the linear regulator plus from the switching regulator.
Sir, sorry to disturb you, but
Yeah.
we are taking 180 in milliwatt and other in watt. So
Yes. Oh,
it
I
would be
have mentioned it milli here.
Okay, sir, we will not convert it into what?
You can, okay. So let me write it as 0.18. Is this fine?
Okay, sir.
So I was writing the small m here to denote milli, but I mean it's okay. Okay. So this is my P out total plus 0.27. That is the P loss from linear regulator plus 0.36. That is the P loss from switching into 100. Okay. So that comes out to be 3.42 by 3.42 plus 0.63 into 100. So that will be equal to 84.4. Okay. So yeah, the first answer was correct. The student who mentioned it. Okay. I'll wait for 1 minute. So if anyone has any question here, so they can feel free to ask me. Okay. Is there any question? Okay. Okay. Is everyone clear with this solution? So I think the first two questions were a bit simple. Okay. So gradually, there are few more questions that we will be covering today. So we have, uh, I mean, a mix of moderate to simple questions. So week 1 is not that difficult, but gradually, uh, the difficulty will go on increasing. So what I suggest is like whatever questions we practice now. So you try to do it. You try to do it along with me, and later on. So anyone, if they find anything to be difficult, or maybe let's say you arrive at a wrong answer. So after this session is over, so I'll be uploading the video. So you can go through that and see what method I used and what method you used. So if you feel that there is a discrepancy and you are unable to understand that, you can feel free to ask me the your doubt is. Okay. Okay. So I'm assuming that there is no doubt in this question. Generally in exam, how much is the weightage for numerical for this course? Okay, so I think the numerical part uh, will comprise of a good amount. Okay, but there is no such weightage distribution that has been mentioned. So yeah, but yeah, numerical is quite important. So I mean, it can come up in like more than one option correct, or some integer based thing in that format. But yeah, numerical will come for sure. So weightage, not sure. Majority will be numerical. So I think in week 1 you have a few questions related to true false in the beginning, right? But if you see later, the later parts are all numerical. Okay. So moving on to the next question. Okay. So the next question is based on line and load regulation. Okay. So a 5-volt voltage regulator indicates that. So there is an indicates that V naught typically changes by 3 millivolt when V in, so this is input, is varied from 7 volt to 25 volt, and by 5 millivolt when I out is varied from 0.25 amps to 0.75 amps. Okay, so basically, we have to estimate the typical line regulation, right? The typical load regulation. Okay. So whenever we have a voltage regulator, we want it to provide constant V out, irrespective of what the load is and irrespective of changing input. Okay, even if the input is, dirty, we want the output to be as clean as possible. So those parameters are quantified using these metrics that is called as line regulation and load regulation. So this question is based on that. Okay. So I'll wait for 2 minutes. You can start solving this question. So after that, I'll try to solve it. In regulation, 1%. Mm, no, probably you need to recheck it. So line regulation is not very. So maybe you can tell it in terms of absolute first, then maybe go to percentage. Because, okay, so there will be a bit of difference when it comes to the absolute and percentage here. So, yeah, be a bit careful about that. Minus 10, 0 point. No. Yes, I got one correct answer. Yes, yeah. Correct. Correct. Yeah, okay. So we can start solving. So I see two correct answers. Load is 10 milli. Yes, correct. Okay. So let us start. So what is our line regulation? Basically, it is a measurement of how much the output varies if the input voltage changes. Okay. So delta V naught by delta I naught. Okay, let me write it as line. Okay. So what is my delta V naught? 3 millivolt. Okay. So 3 milli by delta Vi. Delta Vi we will get it from here. 25 minus 7. Okay, that is 3 millivolt by 25 minus 7 is 18. That is 1 by 6 millivolt per volt or 0.167 millivolt per volt. Okay. Okay. So now there is an interesting thing. So line regulation in percentage. Okay. So that is delta V naught by V naught by delta Vi. In the, okay. What is the V naught here? So V naught is basically 5 volt. Okay. That is why the name 5 volt voltage regulator. Okay. So it will be 3 milli by 5 by what was our delta Vi? That was 18, right? Into 100. 3 milli by 5 is 0.6 milli by 18 into 100. Okay, that is equal to, so 0.6 by 18, that will be somewhere 3.33 milli into 100 percentage by volt. That is 0.0033 percentage. Right. Is this clear? Okay. So this is our line regulation, and this is our line regulation percent. Okay. So moving on to load regulation. Okay. So load regulation means if my load varies by a certain amount, okay, indirectly, what I'm saying is if my load current varies by certain amount, then how much is my output voltage affected? Okay. So that is delta V naught, right? Okay. So my delta V naught is given to me as 5 millivolt when I naught is varied from this much to this much. Okay. So 5 millivolt by I naught is minus 0.75 minus 0.25 amps. Okay. This is 5 millivolt by 0.5 amps is 10 millivolt per amp. Similarly, for load regulation in percentage, we will have delta V naught by V naught by delta I naught, and we'll have 5 millivolt by 5 by our delta I naught was 0.5 amps, right? 100, that is nothing but 9%. Okay, so I'll pause here for a minute. So if anyone has any question, okay, they can let me know. Okay, so for people who got wrong answers, so I'll suggest you to go through this solution that we covered now. Okay, so I can see only two correct answers. So 10 million and 1 by 6. That's actually correct. Right. So 1 by 6 is this one, our line regulation, and 10 millivolt per ampere was our load regulation. Right. So I'll pause here for a minute so that you can digest the current problem that we solved. Is this clear with everyone, or is there a question here? Uh, is there any question? Okay, so let's move on to the next question. So should I pause for a minute or should I move to the next question? Is there anyone who wants me to pause for a minute? Okay. Okay. Moving on to our next question. So in the next question, we are given a 10-volt precision voltage reference that gives a typical line regulation of 0.01% per volt, a typical load regulation of 0.001% per milliamps. Find the variation in V out brought about by a change of Vi from 13.5 volt to 35 volt, a plus minus 10 milliamps change in I. Okay, so this is similar to the previous question that we did. So I'll wait for a couple of minutes so that you can try it out on your own, and later on I'll try to solve it. Uh, yeah, line regulation is 0.001%. Zero point 0.215. Okay, I think you need to be a bit careful about the units. Yeah, I'll wait for a couple of more answers. Let's see, because it was similar to question 3 that we did. We have another answer. Okay, so I'll wait for one more minute, then I'll start solving this. So I think there is some issue with the decimal place. So 215, okay, the numbers are correct, but the decimal places are wrong for two of the answers present in the chat box. Mhm. 2.2 millivolt for B. Okay, is there any other answer? Or question B. Okay, let us start solving it. Okay. It is given that line regulation is 0.001% per volt. Okay. So this means my delta V naught by V naught by delta VI into 100 is 0.00. This implies my delta V naught is equal to, so here what will be the V naught? That is 10 volt. Okay. 2 micro. No, 2 micro is not correct. It will be 0.001 into delta VI into 10. So this 10 is nothing but your volume. Okay. Divided by 100. Okay. So what is my delta VI? So delta VI is 35 to 13.5. Right. So let me write the delta VI first. 35 minus 13.5 into 0.001 into 10 by 100. Okay. 35 minus 13.5 is your 21.5 into 0.001 by 10. That is basically your 2.15 into 10 power minus 3 volt. That is 20.15 millivolt. Okay. So this is for the first one. Is everyone getting this? So I see people arrived at 215 in those digits are fine, but while doing the multiplication, probably somewhere uh, 10 went missing for some people, but it's okay. Okay. So for okay, so I'll wait for the B part because part B I find none of the answers are correct so far. So maybe for part B I'll wait for 1 more minute. So give it a try. Okay, so to avoid confusion, so plus minus 10 milliamps change. So it is actually referring to change. So you need not do plus 10 minus 10 milliamps. Okay. So that's why I guess some people are getting the number 2 there. So yeah. So word of caution, it mentions change here. Okay. And only focus on the magnitude for this part. Okay, yeah. I got one correct answer. So 1 milli is the correct answer. So let's see. So for question B, what is the load regulation given to me? Load regulation is 0.001 percentage per milliamps. Okay, so be careful with the milli part here. Okay, so my load regulation in percentage is delta V naught by V naught by delta I naught into 100. Okay, that is given to me as 0.00. This implies my delta V naught by 10 equals 0.001 times delta I naught by 100. Yeah, and delta I naught is given to me. Okay, so let me only be concerned with the magnitude. Okay, 10 milli into 0.01, sorry, 0.001 by 100. Okay, so another thing, so okay, per milliamps. So I'll just write the milli here. Okay, so this milli gets cancelled out. So I'm left with 0. Uh, this implies my delta. So this is my delta V naught by 10. So my delta V naught will be 10 into 0.001 by 100 into 10. Okay, 10 gets cancelled. So I'm left with, this is my 1 millivolt. Okay. So plus minus 1 millivolt is the answer for part B. Okay. So I'll pause here for a minute. And if anyone has any question, then let me know. Okay. So here, there are few things that you need to be very careful of. So whenever you are given a specification, look out for these terms. Okay. So because we are so used to only ampere or only voltage, right? So whenever we are given some specification with milliampere, like it becomes a bit tricky to us, right? And we go on solving for ampere. So be very careful there. Second thing, note the question very well because here it says change. So it is not saying that it varies from minus 10 milliamperes to 10 milliamperes. It says that the change in I out, that is delta I out, is either plus minus 10 milliamperes. Okay. I guess the answers which had that uh, factor of 2, right? So they were coming because I guess the students assumed that it is changing from minus 10 to 10 or 10 to minus 10, something in that direction. Okay. Is there any question? So I'll wait here for 1 minute. Okay. If there is any question, then feel free to unmute yourself, or else you can type it out in the chat box itself. If there is any question. Okay. So let's move on to the next question. Okay. So I'll wait for a minute so that you can just note down this circuit diagram, and later on I'll show the specs. Okay. So note down all the nodes that I have used here, right? So I hope this is clearly visible. Okay. Once you have noted this diagram, just type it on the chat box that noted. So I'll show the spec. Okay. So with this, you've done noting down the diagram. and this is plus and minus. So I hope this is clearly visible. Let me just zoom out a bit so that you can note down these parameters. Okay, please note down these parameters. Okay. Is it noted? Okay. Then start solving. So we need to find out what should be the value of R2. Okay. To obtain V out desired as 650 millivolts. This is the circuit that is given to us. So this circuit looks a bit familiar to anyone? Yes, correct. So this is a BGR. Okay. So I'll wait for, let's say, 2 minutes. Okay. Maybe this will take, let's wait for 3 minutes, and we'll wait for some answers, and then I'll start solving. Okay. So before jumping into the actual solution, so I have a question here itself. Okay. So I'm using red ink. So I have this current. Okay. So let me call it IC1. And I have this current. Let me call this IC2. I have this current. Let me call it IC3. So what is the relation between IC1, IC2, and IC3? All are equal. Okay. Did anyone arrive at any value for R4? Is there any answer for R2? Okay, I'll wait for 1 more minute and then we will start solving this. If anyone is trying and wants me to pause for more time, so let me know. Else we'll start with the solution. Okay, I think then we'll start with the solution. Fine. So you can see that these two nodes are going to be same. This is Vx and this is Vx. That's why I marked it earlier as Vx. I mean, I have denoted both of them with the same name. Okay. And I am denoting this node as Vy. Okay, just the node above the 10th transistor. Okay. So this Vx is nothing but, so this is my emitter terminal and this is my base terminal, right? So this Vx is nothing but VEB. Let me call it as VEB1. Okay. Similarly, if you look at Vy, let us call it Q2. This will be my VEB. Okay. And as discussed earlier, so IC1 is equal to IC2 equal to IC3. Okay. MP1, MP2, MP3 are identical transistors. Okay. So, okay, I should have mentioned that. But as it was clearly identified that this is a BGR, so it is quite obvious. Uh, okay, so the current flowing through all three branches are going to be same. Okay, so these 2 points are the biggest hints here. Okay, using them, we will solve this question. Okay, so let me write down the equation. So for Vx, that is equal to Vt ln IC1 by Is. Okay, so that Vx is nothing but VEB1 from this equation. Okay. So similarly, we can write for Vy as well. Okay. My 3.03. Quite close, but I think you missed one factor somewhere. I guess you missed a factor somewhere. Okay. Okay, let me call it ICX1. That will be better because IC1 is the current flowing through the main branch. So this one is, let's say, ICX1. Where the video will be. Oh, I'll share that. Just give me 1 minute. So I will be uploading it here. Yeah. So I'll upload the videos in this link. So I have shared it on the chat box. And I'll also share this slide. So I'll create a drive and the drive link will be shared uh, with the NPTEL team. So I think, did you guys receive an Excel sheet where which contains my name or something? Okay. It's okay. Like I think the NPTEL team will share it with you. So that will contain. So whatever I'm writing down, right? So I'll save that and I'll put it in that drive, so you can access it from there. Anyways, the recording will be available on the YouTube channel. Okay. Okay. So my Vx is like this. My Vy will be similarly Vt ln ICX2 by 10 Is. Okay. So why 10 Is? Because the transistor size is 10x. Fine. So my Vx minus Vy is basically ICX R. Okay. So basically I just saw that my potential here is Vx, potential here is Vy. Okay. So my Vx minus Vy is equal to IC X2 R. Okay. This implies VEB1 minus VEB2 is equal to ICX2 R. We call this equation 1. Okay. Also, if you see, so IC2 is like this. This is my ICX2. This is my ICR1. Okay. So I'll have an equation like ICX2 plus ICR1 is equal to IC2, that is equal to IC1, that is equal to IC3. Okay. This implies my ICX2 is nothing but IC1 minus ICR1. Fine. And what is my ICR1? ICR1 is nothing but Vx by R1. Okay, because the node potential here is Vx and R1 is the resistance. So the current flowing through it is ICR1. So I'll write it like that. IC1 R1 minus. So what is my Vx? Vx is VEB1, right? Minus VEB1 by R1. Okay, this is my ICX2 equation. So now what I will do, so I'll substitute the value of ICX2 in my equation. I guess everyone is close to the answer, but by a factor or two, you guys are a bit uh, moved. 31.7K is a bit larger, so maybe you need to recheck that one. Okay, so if I substitute that value at the top, I know my VEB1 is like this. VEB2 similarly, I can write that down. So this is VT ln ICX by IS minus VT ln ICX by 10 IS. Okay. So these two ICX are similar. Okay. Why? Because my IC1, IC2 are same. Okay. And my current through these two resistors, they are also same. Why? Because the potential is Vx at both the positions. So instead of writing ICX1 and ICX2, I can write them as ICX1 equals to ICX2 is equal to ICX. So that is what I am doing here. Okay. That is equal to IC1 minus VEB1 by R1. Okay. Times R. Okay. So this one will be VT ln ICX by IS divided by ICX by 10 IS equals IC1 minus VEB1 by R1 into R. Okay. So this will cancel, IS will cancel. We will be left with VT ln 2 is equal to IC1 minus VEB1 by R1 into R. Okay. So I'll rearrange these terms and I'll only write down for IC1. Okay. So for IC1, I'll have VT ln 10 plus VEB1 R2 by R1 whole multiplied by 1 by R2. Okay. Okay. So let us keep this equation here and let us go to the output terminal. Okay. So what is my V out? Okay. So the current is IC. Okay. IC3. That is basically same as IC1, IC2 and IC3. So my V out is IC times R3. Okay. And what is my desired V out? That is mentioned. This is given as 650 milli. So 650 milli equals, I'll substitute this value here, Vt ln 10 plus VEB1 R2 by R1 into 1 by R2 into R3. Okay. So the value of R3 is already given to us 30K and R1 is given to us as 50K. So just let's do the substitution. 650 milli equals Vt value is also given to us as 26 millivolt. We have 26 milli into ln 10 plus VEB1 was 0.65, I guess. 0.65. 0.65 into R2 by K into R3 was 30K, right? That will give us this R2 gets cancelled. Let me just in this. Okay, so K will get cancelled, 0 cancelled. So I'll have this is 650 milli, so 0.65 volt minus 0.65 into 3 by 6, 3 by 5. 3 by 5 is what? 0.6 is equal to 26 milli ln 10 into 50K by R. This implies 0.65 minus 0.26. So 26 milli ln 10 into 30K by R2 is equal to 0.26. This will give my R2's value, that is 26 milli ln 10 into 30K. So K and milli will get cancelled, divided by 0.26. Okay. So I have 26 into ln 10 into 30 divided by 0.6. That is 6.9 kilo. Okay. Is this clear? So okay, this is a bit of lengthy. So maybe I'll pause for a couple of minutes so that you can ask me any questions. Wherever you have a doubt, please feel free to ask. Is there any question here?
So,
Yeah.
yeah, can you please go to the schematic ones? This is
Yes,
not
sure.
with respect to this question, but like I have a small doubt,
Hmm.
and during the lecture as well. So how do we get these signs of the op amp in a negative feedback? Like before we
Okay.
won't be having like, but how do we get that plus and minus? Like which
Okay.
terminal is plus and which terminal is minus?
So we tried. So what we do is, so for bigger circuits, right? Okay. So let us say there is no op amp and it comprises of MOSFETs and stuff. So what we do is we pick any one position, okay, and we try to go throughout that feedback loop. Okay, so let us assume that I start from here. Okay, let me use red ink. So let us say I start from here. Okay, here or here, anywhere, and I just imagine that this node potential is increasing. Okay, so after assuming something, then I go about, let's say this. Okay, so let us say this is increasing, this is increasing. and because of this increasing, so the current will decrease for PMOS state. So because the current decreases, then this thing, uh, I mean, it goes on decreasing or increasing based on that. Okay. So based on that, we see that if the point that is increasing is being pulled down because of the feedback, then it means it is a negative feedback.
Yes, sir, that's okay. But here we have both, like there is a
Yeah,
conflict
here both
between
are
both the
increasing,
terminals.
but one terminal increases faster than the other.
Oh, okay.
Okay. So, I mean, when such a situation arises, then the terminal which is having a stronger uh, negative feedback, right?
Yeah.
That will be considered to be the negative terminal, and the weaker negative feedback will be considered as the positive.
Okay. When it comes to this circuit, like can we do it in this fashion? Suppose if we are trying to decrease the value of gate of one MP1, suppose.
Okay.
So the current through the MP1 is increases, same as MP2.
Mm, okay.
So the voltage at drain of MP2 will be increasing. As current increases, the voltage drop across resistor will increase. So the
Mm,
voltage at Vx also increases, like I mean drain of MP2.
okay. Mm,
But when we come to the on the right hand side,
mm.
uh, it is also on the same fashion, right? By
Yeah.
by so like how are we sure that keeping these signs will give us negative feedback? That's my question.
Let me do one thing. So, okay, I'll try to get back to you. So, I'll come up with a maybe more intuitive plus a properly quantified answer to this question. Okay, I'm noting this down. Okay, so in the next session, I'll explain that.
Okay, thank you,
Is
sir.
that fine?
Yeah.
Okay. So meanwhile, for this question, just there was some question. No, that's because like so VY will take care of that, right?
Like we are adding these R1 and R2, R1 and R2 to scale the reference voltage basically.
Yes. Yeah.
S- so like I mean, so even if we don't consider the R1 and R1 like R1
Yes.
on Q1 side and R1 on the R2 side,
Uh-huh. Still it will
both
work.
will be having two feedbacks, right? Like how are
Yes.
we sure that these signs will give us negative feedback?
Yeah. Okay, so the negative feedback thing, I'll cover it again in the next this thing. So let me come up with a plausible answer to this. So, okay, is this same person asking the question, or is it different?
No, no, different. Like,
Okay, yeah. For the negative feedback thing, I'll surely come up with a good quantitative explanation, because in this case, both the terminals are actually moving in the same direction. So, okay, I understood that.
yeah, like I'm even not sure about that also, sir. That's the main question. But I don't know how the terminals are swinging. That's the main mention.
Just give me one moment. Oh, okay. I think, yeah. So I think it has to do with the 10x the source present here. Okay, so let us say that this is the positive terminal, right? So let us say I increase the current here. I mean, increase the voltage here. Okay. So I'll have A. So output is A V plus minus V minus, right?
Yes.
Okay. So if I'm increasing the potential in this terminal, then my this voltage is going to increase,
Yes.
correct? And so if this potential increases, what happens to the current that is flowing in this direction?
Decreases.
Okay. So because of that decrease, so if you see that it is going to decrease at a faster rate,
Okay.
okay, in comparison to the transistor Q1.
Okay.
Okay. And because of that reason, so this terminal is going to be assigned plus sign, because this is going to steadily decrease, like not immediately this thing. So, so I mean, so the change in direction of potential in this particular point is actually opposite. Because of the decreasing current, so it will try to pull down this node back to its original position, right?
Okay.
Is
Okay.
that clear?
Mm, I need to think about it, and like if I have any doubts, I will contact.
Yeah. Okay. Okay. Is there any question from this part? Is there any other question? If not, then we can question. So this is question number 6. Okay. So this is actually a question from CMOS. Let us say we have, okay, so let me start with a question from control systems first. Let us say I have a block like this. Okay. So what is the overall transfer function? G by 1 plus GH. Okay. Now, let me say I have an amplifier whose transfer function is A of S. Okay. And I have a feedback factor of beta. Okay. And beta is independent of frequency. Okay. So in this case, what will be my transfer function? A of S by 1 plus A of S times beta. Okay. And it is given to me that A of S is equal to A naught by 1 plus S omega naught. Okay. So basically what I am saying is the open loop response or the open loop transfer function of A of S looks like this. Okay. The question is find the closed loop DC gain. Second, find the bandwidth of the closed loop system. Okay. And I say bandwidth 3 dB. Okay. So please give it a try. Bandwidth is A omega. No. DC gain is A naught by 1 plus A naught beta. Yes. Yeah. DC gain is correct. Which is yes. Bandwidth is correct. Okay. Okay. So let's try to solve this. Okay. So a closed loop transfer function, it looks like this. And it is given to me that A of S is equal to A naught by 1 plus S by omega. So what I will do is I'll write 1 plus S by omega naught by S times beta. Okay. So this will be A naught plus A naught by 1 plus S by omega naught plus naught beta divided by 1 plus S by omega. That will be A naught by 1 plus is by omega naught plus a naught beta. Now let me just take out the entire DC term. So a naught by 1 plus a naught beta. So I'll take this term out from this. Okay. So I'll be left with 1 plus s by omega naught times 1 plus a naught beta. Okay. Now let me call this ADC. Okay. So the term that is situated here. Okay. So earlier, if you see, so this was so omega naught was referring to the bandwidth. Now for the closed loop transfer function, omega naught times 1 plus a naught beta refers to my bandwidth. Okay. And ADC is nothing but a naught by 1 plus a naught beta. So let me plot it. Okay. So let us say uh, this was earlier my a naught. Okay. An open loop this thing. And this was my omega naught. So after let me show the approximation. So my ADC is a naught by 1 plus a naught beta. Okay. And I know that my a naught beta is very, very greater than. Okay. So I can write this equation as a naught by a naught beta, that is approximately equal to 1 by beta. So my ADC is nothing but 1 by beta. Okay. So whenever I close this loop, now it will be 1 by beta. Now my bandwidth is somewhere here, that is omega naught times 1 plus E naught beta. Okay. Is this clear? Okay. So let us revisit whatever questions we covered today. Okay. So we did one question on uh, the efficiency of switching regulator. We were supposed to find out what is the total power loss. Okay. Next, we did a question where we were given specs and we had to find out what is the total efficiency of the power management module. So we had two regulators with us, a linear and a switching regulator. Okay. So I'll suggest you to practice with various combinations. So there can be switching, linear switching. So multiple cases that were covered. So to practice that, okay. Then we covered few questions on line and load regulation. So two variations of the same were covered in question 3 and question 4. And in question 5, we solved a question related to BGR. So in week 2, you can see that this BGR circuit comes into picture. Okay. Then, so at the end, what we were doing is so closed, it's a feedback system. So this thing will be helpful for you in covering your week 2 and I think in week 3 as well. Okay. So you need to brush up your CMOS concepts a bit. So that will be helpful. Uh, okay. So is there any question for the last for this one? Okay. So these were the questions that I prepared for today. So if there are any questions, okay. So because this is the first session, right? So if you guys can introduce yourselves briefly, so that will be helpful. Please feel free to unmute yourselves. No, tomorrow there won't be any classes. So every Saturday, 3 to 5 p.m., we will have this sessions. Okay. So anyone, please feel free to introduce themselves, like in which year you are, and so what is your motivation behind the course. You guys can feel free to introduce and interact. Okay. It seems no one wants to interact. It's okay. So so this is where I'll be uploading the video recorded session, and so I'll also share this entire note which I wrote. So I'll share that. Uh, and yeah, regarding that negative feedback question, so I'll try to maybe quantify it somehow, and I'll show it in the next session, next Saturday 3 to. Okay. Is there any other question? If not, we can wrap up today's session. So, is there any feedback that you want me to know, like were the questions fine? Was my pace fine? Like, was it too fast or too slow or anything?
So it was good. I have one question that एग्जाम
Yeah.
में इसी टाइप के क्वेश्चन आएंगे और it will be something different.
एग्जाम में मतलब जो असाइनमेंट्स हैं उसी के रिलेटेड, एंड मोस्टली जितना जो भी कवर किया गया है आपके लेक्चर क्लासेस में, राइट? सो बेस्ड ऑन दैट इट विल कम. ओके, सो दीज सेशंस आर फॉर योर प्रैक्टिस, कि मतलब आपको वो कॉन्सेप्ट से एटलीस्ट मतलब इंट्रोड्यूस कर सकें कि अच्छा ऐसा होता है, ये होता है. सो या आई मीन, सो दे विल बी हेल्पफुल फॉर योर एग्जाम्स.
Okay, sir.
Is there any other question anyone else has? Take more questions in sessions. Okay, sure. So next session, I'll try to add more questions. Okay, so when you say more questions, are you referring to more numericals, or is there any other preference? Okay, is there any other question or any other suggestions? Some theory part as well as numerical. Okay, so I think that I can do. So I can cover a brief review. Like before starting the numerical, I can cover a brief review of maybe that week's lecture. Okay, so I'll just take maybe 10 to 15 minutes to briefly go through what was covered in that week, and maybe then start the numerical. Will that be fine? More circuit based problems. Yeah, sure. Uh, Suggest books related to these power management integrated circuits. Okay. So there was one book by, hmm, I think in the course page, that book's name was mentioned. Yeah, this one. So, okay, let me copy this one. Yeah, yeah, sure. No problem. So I'll try to cover a bit of theory as well. So I think if I do some review kind of thing, like uh, I mean, I can't cover the complete all the lectures, but I'll just pick the important ones, the important points from those lectures, and maybe that can be a kind of revision. Will that be fine, Surjit? So then, yeah. So this is one of the books. Uh, and yes, so definitely. So CMOS analog by Behzad Razavi, design of analog CMOS integrated circuits. Even that is good source that will help you. So I think three or four of the chapters are very important. Like there was a chapter on feedback, plus I think the op-amp chapter, as well as there was a chapter on voltage regulator. So these three, four chapters will be very helpful. You can go through that. And also, so once you have gone through the lectures, so there is a lecture note that Professor Kadir has uploaded. So let me, so it is present. So in the books section, right? So you can see there is a link called as English book. So if you click that one, so it leads you to a link that can download the uh, basically the transcript plus some additional things that he orally mentions. So that is written down in that book. So you can go through that, and that will help you in revising the lectures. Okay. Are there any other questions, or is there any other doubt? Okay. If not, then we will wrap up today's session. And I have taken whatever feedback you have mentioned. I'll include more problems for sure, and I'll keep some theory part as well. Okay. So yeah. So thanks everyone. We'll close this session. So I'll be here for 5 more minutes. So let me know if anyone has any question that they want to discuss. Okay. Otherwise, we'll meet next Saturday, same time, 3 p.m. to 5 p.m. Using the same link. Any softwares that will be useful? Yeah, one is LT Spice. So there is an open source software called as LT Spice. Um, so I have used NG Spice as well, but NG Spice is a bit cumbersome. So I'll suggest you to stick to LT Spice if possible. So maybe towards the end of week 12 or something. So I can cover a demo session, means how to use LT Spice, how to use the model files and stuff. So whatever circuits you are basically analyzing, you can simulate them using those softwares. Is there any other question? Okay. Okay. So thanks everyone for joining. We will wrap up for this session.